Yeah, I did not do anything. Now you will have Thibaut and Hugo speaking, and this is their first ever conference and their first ever talk. So they are still students, and at Telecom Nancy, where I teach a bit, Suricata and other stuff. And so I led them, coached them into a project with Suricata to find bugs because fuzzing does not find enough bugs in Suricata. Thank you.
Thank you, Philippe, for the introduction. So as Philippe said, we work on finding bugs in Suricata. And for that, we used a tool which is called CodeQL. So, first, what is CodeQL? Well, CodeQL is a static analysis tool which is developed by GitHub. It can be executed over several languages or over large number of projects which contain C, C++, C#, Java, Python, JavaScript, TypeScript, and Ruby and Golang language. And well, it's centered around writing queries to find some bugs, which are generalized through the .ql language. Well, the .ql query language is an object-oriented query language, and it's used to represent your code in a relational way as an AST. And it was originally developed by Semley, which is now owned by GitHub. And well, now to use CodeQL, you first need to compile your project with it, and after that you'll get a database which will be optimized for executing queries over it, and after that you will be able to ask the database for the information you're searching.
So now I will present to you the methodology. So what is a request in CodeQL, how it works, and how we created our request for our project. So we split our finding of bugs in different steps. So first we search bugs, then we write the query, and then we tested it. And when we ended that, we try to integrate our query to GitHub. So if you go to the CodeQL GitHub, you'll find our query and every query that's been done for CodeQL right now. So finding bugs on Suricata was pretty difficult. So we use GitHub and Redmine, but because most of the bugs have been fixed, we needed that part. We needed a bug that was fixed and that was easy to understand for us to actually create a query. So when we found the bug, the big issue was identifying the problem. So this is the example that we used to create our query. So you see the first one is just an object not freed. The second one is a bad int, and so we use a int too big for the tab. We can actually use a smaller int, which is just a little optimization for CodeQL, for Suricata, sorry. And last one is a useless test, a test that is always true and that can be simplified. So what does a query look like in CodeQL? A query looks like that. It's not very pretty, but it's one of our query. This one is the query for the useless test. But let's split this query more simply. So as you see, maybe you have a from, a where, and a select, like in SQL or any other QL language. So the from in CodeQL is is used to give you every part you are looking for. So, for instance, if you go back to the last one, you have a logical end expression, which is just the end in your if, and it's the from allows you to create this variable and to work with this variable in your where or in your select. The where is the part where the magic happens. You have you create everything. You create the logic that you want behind your query to find what you really need, and the select is just the display for your query. You have also another little part of CodeQL which is called predicate, and a predicate is just a function that can return elements or just true or false, and that helps you create a simpler query and improve how your query is readable. When everything is done, we had to work on the integration for CodeQL in GitHub. So we added just a little metadata and a QHelp to help understand what your query do, how they found bugs, and what can be the solution for the bugs. And that's where the metadata and the QHelp comes in. So now I'll show you our queries and results that we had. So we run our query using LGTM and on Suricata. So most of the bug we found was on LGTM. We only found 2 bugs in Suricata with our query, and we fixed them. We asked for pull requests to fix them. So LGTM is it's just a website that allows you to launch queries on a lot of open project on GitHub. So people can put their project from GitHub on LGTM, and after that, everyone can run queries on it if we want to test it, if we want to find maybe false positive, or that's why we use LGTM, or just to help people improve their code. So so LGTM looks like that when you run a query. So as you can see, we run a query on 1,000 project, almost 2,000, and it took a lot of time to run all our queries on it, and it helps every chart that you'll see in the next step will be taken from every query that we run on LGTM. So first, for the useless test, as I talked before, so you can see that in this case, we have 2 aspects of the test. So in the same if, like a equals 7 and a is different from 8. And as you can see, the a is different from 8 is totally useless because if a is equal 7, it can't be 8. So that's how you correct the bug, and that's what we put in your query to show people. And on Suricata, we found this bug. So it was found first on GitHub, and after that we ran the query on the last version of Suricata, and we found it again on another part of the code. And as you can see here, we have exactly what we want. So after that, we run it through LGTM, and we found 7% of false positive and 93% of true positive. So that's on every test that return a value. Obviously, most of the test was they didn't find anything, and this helped us to improve our query. So that's how we worked. And for instance, one of the false positive we had was using the OR sign because of how we created a query. We wasn't thinking about how, we were just thinking about if they have the same if parents, but not if they had OR between them or not. So obvious mistake. We corrected later on, and the query now works even if you have an OR some of other things like that. Now for the bad integer, so as I talked before, the bad integer is just an improvement. It's not really a mistake. So this one actually triggered on a lot more projects. And it's just, in this case, you just can use uint 8 to access your tab, because your tab is just small enough for uint 8. And it improves just your memory, how your memory is used in your program. So here the correction. And it shows a lot of issue on obviously on Suricata. I think if I remember well, it was 56 issues on Suricata, and on other projects we had 22% of false positive and 78% of false. Sorry, the inverse. So most of the false positive that we had was on double dimensional variable. So here we have the query thought that we are accessing the second part and not the first one. So that's why he didn't think that the uint 16 wasn't useful.
So then I'll talk about the two other queries we've written. Well, the first is about the unfreed memory in a loop. As you can see here, in this case, once we have I equal to, we break out of the loop and don't free the array, which is a mistake which will give unfreed memory. And so for that, well, the obvious fix is to put a free right before the break, and well, so we wrote the query, and well, we found this issue in quite a lot of projects. I don't remember how many exactly. 600? 600 projects out of 1,800. Yeah. Well, among these alerts, we got about 70% of true positives and 30% of false positives, which were usually of this form, as in when an array and a for are in the same the same implication, and you break out of the second for, and well, the query thinks you actually skip the free, which is not the case. Then we have the risk overflow on a comparison. So on that one, there is a risk of, if you have the maximum integer for the maximum uint for a comparison. If you increment it, well, the comparison may become false. And well, the way to change that is to simply use superior of equal or any comparable operator, like inferior or equal, for example. And well, so we're on this query on the projects. And don't have the chart, but there were two projects which were affected. Well, both were true positives, and through several tests, we found some false positives. As which was it again? Don't remember. Oh yeah. don't remember. Yeah, so sorry.
To conclude our project, so as we see, we had another we had another man with us. He didn't come today, but he's with us. Yeah. And we created 4 queries based on Suricata bug and vulnerabilities. We didn't deep read down to find how to create these queries and these bugs, and that's a big plus for CodeQL, because it's pretty easy to understand, and you can easily create your own queries to find the bugs that you found maybe on Suricata. And but also CodeQL is pretty limited for some reason. You can't really create a query on a specific object that you created by yourself. You need to stick to the simple part of code, like int, string, or other simpler variables and type. And you can't really use objects that you created in your code, so that creates a big limit when you are looking for bugs in Suricata. So thank you for listening to us.
Do you have any questions?
Where is the question?
So how should I invoke this if I want to run it on my project?
So as we said in the beginning, if you want to run it on your project, you need first to install CodeQL, and after that, we use VS Code to create the query, and the VS Code extension is very well made, because you only have to, you can create your query, add your database, so it's just a command line when you compile your code, and you can execute your query very easily if you want. So just basically install CodeQL and create your own database. After that, the query will run smoothly if you use like extension like VS Code, or you can run without with command line if you want.
Thank you.
Hello. Hello. When you do a check if I+1 less than 256.
Go back to the slide of the last.
Your teacher is making me do this, by the way.
She asked me.
So when you do if I+1 is less than 256, the I+1 is not exactly stored in I. So how does it overflow?
So for this false positive, we have the issue understanding really it when we found it first, because when we found it during our project, we were looking at it and like, but it's true. I mean, I+1 is true basically, but the fact that you have I don't remember really how we found out that can't work. You can't have this over too far. I think it was because of the ++y, which is creating, which is not working like we thought it would. But I don't really remember well. Sorry for that one.
So let me add something to that maybe I should have said in the introduction, but maybe this kind of project is also part of open source karma, because we use the experience that we have on Suricata bugs to reproduce on thousands of projects to find bugs in all these projects, and so that's, yeah, I think that's a good way to contribute to all open source. Thank you.